Okay, this is worksheet 3, number 6. So I'm not going to retype it, and you already should have the diagram. I'm not going to redraw either the diagram or the given find. It does tell us that an amusement park ride operates as follows. Riders enter the cylindrical structure when it is stationary with the floor at the point marked A. They then stand against the wall as the cylinder then begins to rotate. When it is up to speed, the floor is lowered to the position marked B, leaving the riders suspended against the wall high above the floor. So this is very similar to a gravitron. The only difference with this and a gravitron, the gravitron is going to have walls slanted, whereas this is a rotor. The rotor has walls that are straight. So it's a little bit less complicated than if it actually was the gravitron, because the walls are straight as opposed to slanted. So we don't need those. It tells us to determine the period of rotation necessary to keep the riders from sliding down the wall when the floor is lowered from point A to point B. It tells us that the radius is 1.5 meters, so given find, you can just write the word given above those values. So it tells us that the radius is 1.5 meters, that the coefficient of static friction, so that's the mu s, is 0.50, and the mass of the person, boy, I think that's what the B's for, the mass of the person is 73 kilograms. Okay, so underneath the picture it says to determine the period of rotation, so what we're looking for is T. We'll start with a force diagram. The easiest place to look at this force diagram is if we just look at the person on the right or the left. So although in the picture it shows the person looking straight at us, let's make the center of the circle over here. So if center is here and we draw our force diagram, we'll have weight going straight down. Keeping the person from sliding down would be a frictional force going up, and that frictional force has to equal the weight. And then if center is to the left, that means the person is on the right. The surface for the person is the wall. So that means that the force directed towards the center, perpendicular to the surface, is the normal force. So again, this could be drawn really in any orientation, because as they go around, the center will always be in the same direction as the normal force. I just found it easier if we were to draw the person as if they were on the right hand side, the normal force would be pointing to the left, which is the direction of center. From my force diagram, I know that frictional force is equal to the weight. So frictional force equals mg. And we know that frictional force is equal to mu Fn. So mu Fn is equal to mg. I know that my centripetal force is equal to right minus left, so 0 minus my normal force. And I know that centripetal force is also negative because it's directed to the left. So those negatives will cancel out, and we know that centripetal force is equal to normal force. mv squared over the radius equals my normal force. And coming back over here, what we got from frictional force equaling Fg, we can rearrange this to say that Fn equals mg over mu. So substituting this in, we get mv squared over r equals mg over mu. M's cancel. I'm just going to go over the next. V squared over r equals g over mu. We're looking for period, and if you recall, the only equation that has period in it is the equation for speed, v equals 2 pi r over t. So by finding speed, I'll be able to figure out what period is by rearranging to t equals 2 pi r over v. So let's finish solving for speed. V squared equals rg over mu. So v equals the square root of rg over mu. Putting these numbers in, v equals the square root tells us that the radius was 1.5 meters. G is our constant, 9.8 meters per second squared over mu 0.50. This equals 5.42, keeps on going, meters per second. Not what we're solving for, so we're not going to round it. Now coming back over here, period equals 2 pi times the radius, 1.5 meters, divided by my unrounded speed, so 5.42 keeps on going, meters per second. This will give me 1.73, keeps on going, seconds. Only one sig fig, so the period is approximately equal to 2 seconds. This is similar to the wrecking ball problem in that you had to figure out speed in order to find period, but that's the only way. You'll notice that mass canceled, so it's not always going to cancel, it's not always going to be irrelevant, but in this case it was. And the main thing to remember is that frictional force has to equal Fg because your surface is up-down as opposed to horizontal. So having a vertical surface means that friction has to point up to keep the person from sliding down, and your normal force must be what's pointing right-left. Again, it didn't matter what way you had that normal force pointing. The easiest thing to do, though, was to make it point either right or left. Either way, though, wouldn't have mattered since that's the only force acting in the direction of the circle.